Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is the fourth edition, and we are in chapter 8, which deals with water movements. And more specifically today, we'll be looking at combined processes, mixing, and ecological implications. Wind forcing and buoyancy flux, that is heating and cooling and internal wave motions, act continuously to modify the stratification within lakes and the fluxes of biogeochemically and biologically important scalars. Examples of the forcing thermal stratification, buoyancy, frequency, and eddy diffusivities have been provided. Influence of turbulence on solute fluxes. In the following, we illustrate the changes in turbulence as the rate of dissipation of turbulent kinetic energy, sigma, and overturning length scales, eddy sizes in Lake Pleasant, New York. Changes are illustrated with respect to the turbulent velocity scale for wind, U star W, and the turbulent velocity scale for cooling, W star, computed from heat loss, and the depth of the mixing layer, W star, is equal to BZ to the power 1/3. The lake illustrated in figure 837 illustrated in figure 837 were taken after several windy days that caused the upper mix layer to downwell to the bottom of the northern basin and then upwell. The lake number was less than 1, and stratification weakened with the ensuing mixing. Cloudy days and cool nights further contributed to the weakening of the stratification. Upwelling combined with cooling such that turbulent eddies entrained CO2 from the seasonal thermocline led to increased concentration of dissolved gases in the upper mixed layer of Lake Pleasant. With a shift in wind direction, the seasonal thermocline with elevated concentration of CO2 upwelled at the measurement site, afternoon of DOY 275. So this pretty much describes what's going on with that Lake Pleasant in that figure. So why don't we jump right into the figure here. So figure 836, conceptualization based on Kolmogorov microscales N and Batchelor length scale LB of fluxes of dissolved gases across the air-water interface. SC is Schmidt number, sigma is turbulent kinetic energy, and V is kinematic viscosity. Concentration in the water near the interface are illustrated with the green line. The thickness of the viscous sublayer at the air-water interface scales with the Kolmogorov microscale for length. The concentration gradient occurs over the diffusive sublayer scaled at the Batchelor length scale. Dissolved gases with concentration Cb is transported by the small-scale eddies to the interface where concentrations are in equilibrium with those in the atmosphere. Flux at the interface over time, F0, T, occurs where there is a difference in concentration. The upward transport is conceptualized as a renewal event whose duration is the Kolmogorov microscale for time, tau in figure tau K in text. The remaining gas after time T, Ct concentration at the air-water interface. Several renewal events are scaled as C over Cb, Z is depth. So I think what we're looking at here is a lake. So this is a cross-section of a lake. And this is the air. This is the surface of the lake. This is probably the thermocline, I would think. And then those little bubbles here are, I believe they are like dissolved gas, and very likely maybe CO2, as mentioned in the text, although they don't mention what kind of gas that is. And so it looks like the cycling of that gas that is dissolved in the water through time. Okay, let's look at figure 837 here. Time series of turbulent velocity scales for A cooling, W star, and U star W, temperature contours, C CO2 concentration, parts per million, ppmv, D logarithm of sigma, and E logarithm of centered overturning scales. maximum overturn in size in the middle of the eddy. And so let's look at this. This is the wind speed in meter per second, and then we have the wind cooling W star, and then this is the wind U star W, I believe, in meter per second. So this is a cooling flux that is purple, and the wind speed that is black. Then we have the temperature profile. So this is over 2 days and 275 days. That would likely put us in September. And so we have a heating event here, and we have a depression of the thermocline with depth. So this is the surface, this is the depth. This is a pretty shallow lake. Looks like it's about maybe 15 meters deep, or maybe 10 meters deep. And so we have a cooling event, we have a warming event, sorry, then we have a cooling event. We have a pretty good thermocline in here, right here actually. And then we have the concentration of CO2 on this one, carbon dioxide. So there is an event here that is outputting carbon dioxide into the water. So potentially like the oxidation of sediments and the generation of CO2 in that process. Then here we have the sigma, meter square per second cube, and so that is, let's see here, logarithm of sigma. So this is logarithm of sigma, and E logarithm of centered overturning scales. So this is a logarithm of centered overturning scales. And when we looked at sigma, it talked right about here. We have the kinetic energy sigma right here. So this is a kinetic energy of the parcel of that specific parcel of water due to its heat content and the fate of it. So actually, they are telling us right here that it's in October, October 2010. Okay, let's see. Why don't we see, these combined processes will likely be important for entrainment in many lakes. That said, the intense mixing associated with lake numbers dropping to values below 1 has led to large increases in CO2 concentration in the surface waters of Toolik Lake in the Alaskan Arctic. Hence, both wind-driven and convective motions can lead to the entrainment of solids. Relation of small to large scale of turbulence. A key concept in turbulence is that the small scales are related to the large, with sigma is equal to U cubed over L, representing the relation. Taking the near surface dissipation rate of N1 by 10 to the minus 6 meters squared per second cube around noon on DOY 276 and overturn scales of 0.1 meters in Lake Pleasant and solving for U gives 0.05 meters per second, similar to U star W. Doing the same calculation under cooling is using the measured value of 1 10 to the minus 7 meters squared per second cube at the surface and length scale of 6 meters. U is equal to 0.008 meters per second, which rounds to 0.001 meters per second, similar to W star. Thus, the large and small scales of turbulence are related. Additionally, the turbulent velocity scales computed from dissipation rates and overturning scales are similar to those computed from meteorological measurements, that is, speed, wind speed, and buoyancy flux. The calculation Kz is approximately UL is reasonable, where L is the depth of the overturn. These are usually much smaller under heating than cooling, such that within the upper mixed layer, Kz can be one of the two orders of magnitude higher, can be one or two orders of magnitude higher under cooling than heating. So why don't we look at DOY 276 here? Taking the near surface dissipation around noon and overturn scale of 0.1. So let's see what's going on at 276. So day 276 is right here. And during that time, we are in the middle of a cooling event according to this. And, and we can see, I guess, the temperature starting to cool at the lake here, although there's some inertia because the coolest is really in that zone, or in that zone, of course. In terms of CO2, that also seemed to have started to trigger a CO2 release here, because we have a CO2 concentration pretty high in this area. And then the sigma is right here, so we have like the value of the kinetic energy that actually is in a zone that was not calculated as far as I can tell, because it's white and we don't have anything for whites. We only have those kind of area here, which probably indicates the overturning event. So this overturning here and overturning there. Timescales for mixing can be LU, L divided by U, L squared divided by Kz. Here, great care must be taken. The mixing efficiency of shear-driven flow as occurs during stratification is lower than that driven by cooling. Under cooling, L divided by U is approximately 10 minutes based on the length scale of 6 meters and velocity scale of 0.008 meters per second, as calculated above. That is a parcel of water which circulates throughout the 6 meter deep upper mix layer in around 10 minutes. Under heating, it would be more appropriate to do the calculation as L squared over Kz, with Kz carefully calculated to take into account the lower mixing efficiency. Influence of turbulence on fluxes of dissolved gases. Dissipation rates, as in figure 837, can be used in calculating fluxes of dissolved gases for studies of metabolism for carbon budgets in streams and in lakes, and wind speeds are light to moderate. Gas fluxes F are calculated as F is equal to K by CB minus CS, where K is a gas transfer velocity and CB is gas concentration in the water, often notated CW, and CS is the gas concentration at the top of the interface in equilibrium with the atmosphere, often noted CEQ. Gas transfer velocities depend on turbulence sigma when wind speed are below those that will induce breaking surface waves, with the incidence of wave breaking increasing as winds increase above 8 meters per second. So your gas flux is equal to K, which is a gas transfer velocity, by CB, a gas concentration in the water at the point X, at the depth X, and CS at the surface. So you subtract the concentration at that depth from, like, you subtract the concentration, sorry, at the top, at the interface of the, from the concentration of at the depth. So gas transfer velocities are modeled using the surface renewal model of K is equal to C1 sigma V by a power of quarters SC minus N, where C1 is a coefficient of 0.4 of EV to the power of 1/4, is the Kolmogorov microscale for velocity. So this is more velocity stuff. So why don't we look at this table? Typical dissipation rate at night, rates at night and in the day for Lake Pleasant in figure 837, and calculated Kolmogorov microscale for velocity Vk. The Batchelor length scale LB and gas transfer velocity K600 computed with the surface renewal model. The convention units for gas transfer velocities are centimeter per hour, and for purposes of comparison are normalized using the Schmidt number to values for CO2 at 20 degrees C. So that may be useful if you conduct such calculation. All right, so advection mixings and inflows. Evaluating the combined influence of the advection, mixing, and inflows on biological and biogeochemical processes can be approached by experimentation or modeling. For example, assessing whether stream inflows moderate primary production requires a number of measurements. These include measurements of discharge and the concentration of nutrients in the stream. This information allows the calculation of the nutrient loading to the lake. Meteorological and time series temperature measurements would be obtained so that graphs and calculation could be done as in the chapter 7. Sampling would also be done on transects. The profile data can include conductivity, temperature depth profiles, as well as microstructure profiling and samples from nutrients, phytoplankton, and primary production. Instrumentation can be placed on arrays along and adjacent to the expected flow path of the incoming water. Similar approaches can be applied to quantify the effects of storm events with their increased winds and mixing. Studies designed to quantify lake metabolism would have a similar design with the instrument arrays including oxygen sensors. Example of such study I found here. Time scale and simulation approaches to assess geochemical and biological outcomes. Predictive approaches include computing timescales for advection, diffusion, and reaction rates. By comparing the different timescales, the dominant fluxes can be determined. Timescales for advection and mixing were presented in section 1. The ratio of transport and transformation timescale is known as the Dam-Kohler number. So those authors use this approach to address whether sinking phytoplankton can grow when the euphotic zone is turbulent. O'Brien determined that only a small fraction of the sinking cells had their residence time increased by turbulence, and that growth and bloom would only occur if growth rates were sufficiently rapid relative to sinking rates. These approaches can be applied to diverse lakes. If typical advective flow speed are known, if values of the coefficient of eddy diffusivity are known to be computed, turbulence and its measurement, and if growth rates as a function of irradiance are known for the phytoplankton community, similar approaches can be applied to predict community structure and energy flows under the ice in winter. Simulation can be conducted on the basis of the 1D equation for change of solute concentration C with depth given in section 2. dC over dt is equal to kz by dt z over dz squared minus u by dc over dz. So here we are looking at the change in concentration over time with our kz, which is a coefficient of eddy diffusivity, and we're looking at a concentration square change divided by over time square minus u, the velocity, velocity, I believe, probably of the wind maybe, and then a change in concentration over depth. Coupled horizontal and vertical movements influence the functioning of aquatic ecosystem. Upper mixed layers are not always fully mixed, and when winds are strong enough, horizontal advection may modify concentrations of nutrients and microbes. For example, during the high winds over Mono Lake in September 2007, the time scale of vertical mixing was 11 hours, and the actual more rapid deepening of the mixed layer resulted in part from horizontal advection, as in figure 8-20. High-resolution profiles of fluorescence indicative of algal biomass showed increases and decreases with subtotal less than 0.05 degrees centigrade, changes in temperature implying advection of phytoplankton of different concentrations from near-shore regions. Similarly, when Vanderburn and lake numbers decrease below 1, exchange can occur between the epilimnion and the hypolimnion. In productive lakes with nutrient-rich hypolimnia, nutrient fluxes may be larger than predicted from eddy diffusivities calculated from 1D approaches. Similarly, in oligotrophic lakes plankton communities in the euphotic zone may be diluted, consideration of these coupled processes will lead to improved understanding of controls on ecosystem structure and function. So that will be it for today, and we'll pick it up tomorrow with section 4, modeling water movement. Thanks, and talk to you soon.